Today we're going to be analyzing the function f of x natural log of x plus 1 in the interval of 0 to 4. Any logarithmic function, the argument, which is a value inside the logarithm, must be positive. So in our case, the argument is x plus 1, so we can solve the inequality by setting x plus 1 greater than 0 and then subtracting 1 from both sides. And we get x is greater than negative 1. This means the domain of f of x is all numbers greater than negative 1. It's a continuity analysis. For a function to be continuous at a point, three things must be true. The function gives an actual value at that point. The left and right sides of the function head to the same value as you get close to the point. The value of the function matches the limit. Calculating left and right hand limits. So we want to find the value of f of x as x approaches 4 from the left side. So we would plug in 4 for x, and that would give us natural log of 5, which is approximately 1.609, so that would be the left-hand limit. And we do the same for the right-hand limit, or the right-hand side. We would plug in 0 for x, and which would give us natural log of 1, which is 0. So 0 would be our right-hand limit. Logarithmic function, natural log of x plus 1 is continuous on its domain of x is greater than negative 1. Since the interval of 0 to 4 lies completely within the domain of f of x, the function is continuous on this interval. The derivative of any natural log function is 1 over u, and u being the argument or anything that's inside the parentheses. So in our case, u would be x plus 1. The derivative of natural log of u is 1 over u, so we get 1 over x plus 1. So we multiply the derivative x plus 1, which is 1. So the first derivative is 1 over x plus 1. To find the second derivative, we use the quotient rule. This involves multiplying the denominator by the derivative of the numerator, then subtracting the numerator times the derivative of the denominator, and then dividing the result by the square of the denominator. So we did that here, and our second derivative is negative 1 over x plus 1 squared. Function natural log of x plus 1 has no critical points because its derivative, 1 over x plus 1, is never equal to 0. Critical points occur when the derivative is either 0 or undefined, since 1 over x plus 1 is never 0, and it is only undefined at x equals negative 1, which is outside the domain. There are no critical points for the function. Find inflection points. We need to find the second derivative of the function, determine where the second derivative is either 0 or undefined, and check if the second derivative changes sign at those points. It occurs where the second derivative changes from positive to negative or vice versa. We can test this by setting the second derivative equal to 0. However, in this case, the second derivative is always negative for all values greater than negative 1, which is the domain of the function. Since the second derivative does not change signs, it's always negative, there are no inflection points. Increasing and decreasing intervals. A function is increasing where its first derivative is positive, and a function is decreasing where its first derivative is negative. Derivative is always positive for any values greater than or equal to 0. So as you can see here, we plugged in 0, it would equal to 1, which is positive. If we were to plug in 1, it would equal to 1/2, which is still positive. As x increases, the first derivative continues to stay positive because the denominator increases, but the numerator remains constant. Because the numerator is always 1, the function will forever increase on any given interval. Because the first derivative is always going to be positive, this means the function will never decrease. To determine the concavity, we analyze the sign of the second derivative. If the second derivative is greater than 0, the function is concave up, and if it's less than 0, the function is concave down. The second derivative is negative 1 over x plus 1 squared. Since the second derivative is always negative for any value greater than -1, the function is concave down across its entire domain. So as you can see here, no matter what value we put in that's greater than -1, the result is always going to be negative. So next, we can solve an optimization problem involving a bacteria population using the given function. The population is modeled by the function p of t equals natural log t plus 1, where t is the time in hours. And our goal is to find how much the population grows over 4 hours. So first, we must find the derivative of p of t. The derivative tells us the rate of change of the population over time. And the first derivative equals 1 over t plus 1. Next, we can find the critical points, but this equation has no solution because the fraction 1 over t plus 1 can never be equal to 0, so there are no critical points to consider. Next, we can evaluate the function at the endpoints of the interval. If we plug in the endpoints of the interval for x, or for t, I mean, it would equal to 0 and 1.6094. So in the 4-hour time period, the population grows by approximately 1,609 bacteria. These are all the key features we need to graph the function. So first, there are no critical points since the first derivative never equals 0. And the end behavior, the function increases from 0 to 1.6094 over the interval. There is a vertical asymptote at t equals -1, but this does not affect the interval 0 to 4. The function is always increasing on the interval. Since the first derivative is always greater than 0, the function is concave down on the interval because the second derivative is less than 0, or the second derivative is negative for any value greater than or equal to 0. The graph starts at 0, increases and reaches 4. It is concave down, meaning the rate of increase slows down as t increases. This is the graph of the function. Next, we're going to find the indefinite integral using integration by parts. So we can use this formula here, and u is equal to natural log of x plus 1, and d of u is 1 over x plus 1, which is the derivative of u. Next, d of v is equal to 1, and v is equal to x, which is the integral of dv. So we're going to plug in everything to the formula, which leaves us with this highlighted portion. And then we need to simplify this box portion, which we could do that by splitting it into 2 fractions, leaving us with 1 minus 1 over x plus 1. Split this into 2 integrations, and since they're both negative, it would equal to positive. So now the integral of d of x, or dx, is x, and the integral of 1 over x plus 1 is natural log x plus 1. So now you could factor out the common terms, and you're left with natural log x plus 1 times x plus 1. And your final result is this box portion down here. Now to find the definite integral, you set your limits to 4 and 0, where the upper limit is 4 and the lower limit is 0. You plug in those limits to the indefinite integral. So if you plug in 4 for x, it would leave you with 5 times natural log of 5 minus 4. And if you plug in 0 for x in the lower limit, it'll equal 1 natural log of 1 minus 0, which is 0. Then you just subtract both of them, both upper and the lower limit, and it will leave you with 4.047. The area under the curve means is basically the total sum of functions values over the interval. And in calculus, this area is a visual representation of the integral.